Close your eyes for a moment and picture the universe as a vast, silent ocean. Now imagine dropping a pebble into that ocean. The ripples spread out, gently disturbing the stillness, carrying energy across the surface. What if I told you that the universe itself creates ripples like these, not in water, but in the very fabric of reality? These are gravitational waves, mysterious ripples in spacetime, first predicted by Albert Einstein over a century ago. For decades, they remained hidden, a cosmic secret waiting to be uncovered. Then, in 2015, scientists made history by detecting these waves for the very first time, opening a new window into the cosmos. These waves are not just scientific curiosities, they are whispers from the most violent and energetic events in the universe, from colliding black holes to exploding stars. Tonight, as you drift into sleep, let's explore the science behind these cosmic ripples, unraveling the mysteries of space-time and the universe itself. And as we begin this journey, I'm curious, where are you joining us from, and what time is it there? Let me know in the comments. Now, let's dive into the dreamy, awe-inspiring world of gravitational waves. Now turning to the heart of the matter, let's explore what gravitational waves truly are. Imagine space-time as a vast, invisible fabric, stretching across the universe. When something massive moves like two black holes spiraling toward each other, it creates ripples in this fabric, much like the ripples you see when you drop a pebble into a pond. These ripples are gravitational waves, traveling outward at the speed of light, carrying energy and information about the events that created them. But unlike water ripples, these waves are incredibly subtle, so faint that even the most sensitive instruments on Earth struggle to detect them. They are born from the most violent and energetic events in the cosmos, colliding black holes, merging neutron stars, or the explosive death of massive stars. These waves are not just ripples in space, they are ripples in time itself, stretching and squeezing the very fabric of reality as they pass through. By studying these waves, scientists can peer into the universe's most hidden corners, uncovering secrets about black holes, neutron stars, and even the origins of the cosmos itself. Gravitational waves are more than just a scientific discovery. They are a new way of seeing the universe, a cosmic language that whispers the stories of the stars. Now turning to the genius behind the theory, let's delve into Albert Einstein's ground-breaking prediction of gravitational waves. Back in 1916, Einstein proposed the existence of these ripples in spacetime as part of his general theory of relativity. At the time, the idea was revolutionary, a bold claim that the fabric of the universe could stretch and ripple like a cosmic drum. But Einstein himself was unsure if these waves could ever be detected. He even wrote a paper in 1936, suggesting they might be too faint to observe, only to later retract it. Despite his doubts, his theory laid the foundation for one of the most profound discoveries in modern physics. It took nearly a century for technology to catch up with Einstein's vision. The tools needed to detect these subtle waves, lasers, mirrors, and incredibly precise instruments, simply didn't exist in his time. But Einstein's legacy wasn't just about predictions. It was about reshaping how we understand the universe. His work on relativity transformed our view of gravity, showing it wasn't just a force, but a curvature of spacetime itself. And while Einstein never lived to see the first detection of gravitational waves in 2015, his genius continues to guide us as we unravel the mysteries of the cosmos. His story reminds us that even the most abstract ideas can lead to discoveries that change the way we see the universe. Now turning to the very fabric of the universe, let's explore the concept of spacetime, a four-dimensional tapestry woven together by space and time. Imagine spacetime as a vast, stretchy sheet, like the surface of a trampoline. When you place a heavy object, like a bowling ball, on this sheet, it creates a deep dent, bending the fabric around it. This is how massive objects, like stars and planets, warp spacetime. But spacetime isn't just a static backdrop. It's dynamic, capable of rippling and vibrating. When colossal cosmic events occur like two black holes colliding or neutron stars merging, they send shockwaves through this fabric, creating ripples that travel outward at the speed of light. These ripples are gravitational waves, carrying energy and information across the universe, much like waves spreading across the surface of a pond after a stone is dropped. The beauty of this cosmic fabric lies in its ability to stretch, bend, and ripple, revealing the hidden dance of the universe. Through these waves, we're not just observing the cosmos, we're listening to its heartbeat, feeling the vibrations of events that happened billions of years ago. Spacetime, in all its elegance, connects us to the farthest reaches of the universe, reminding us that even the most distant events can leave a mark on the here and now. Now turning to the cosmic events that give birth to gravitational waves, let's dive into the extraordinary phenomena that send ripples through the fabric of spacetime. One of the most powerful sources of these waves is the collision of black holes. When two black holes spiral toward each other, locked in a gravitational dance, they eventually merge in a cataclysmic event. The energy released during this merger is staggering, equivalent to converting several times the mass of the sun into pure energy in a fraction of a second. This energy ripples outward as gravitational waves, carrying the story of the collision across the universe. Another dramatic source is the collision of neutron stars. These incredibly dense remnants of dead stars, each about the size of a city, but with the mass of our sun, can also spiral together and merge. When they do, the collision not only produces gravitational waves, but also sends out bursts of light and other forms of radiation, creating a cosmic fireworks display visible across the electromagnetic spectrum. This combination of gravitational waves and light, known as multi-messenger astronomy, allows scientists to study these events in unprecedented detail. Supernova, the explosive deaths of massive stars, are another source of gravitational waves. When a star exhausts its nuclear fuel, its core collapses under its own gravity, triggering a shock wave that rips through the star's outer layers. This violent explosion sends shockwaves through spacetime, creating gravitational waves that carry the story of the star's final moments. Each of these events, black hole mergers, neutron star collisions, and supernova, releases immense amounts of energy, warping spacetime and sending ripples across the cosmos. These waves travel at the speed of light, carrying with them the secrets of the universe's most extreme events. Through gravitational waves, we're able to witness the universe's most dramatic moments, even if they occurred billions of years ago. As we continue to explore these cosmic ripples, we uncover the hidden stories of the universe, one wave at a time. Now turning to the groundbreaking moment that changed our understanding of the universe forever, let's explore the Laser Interferometer Gravitational Wave Observatory, or LIGO. In September 2015, LIGO made history by detecting gravitational waves for the very first time. This monumental discovery confirmed a prediction made by Albert Einstein a century earlier and opened a new window into the cosmos. So, how does LIGO work? At its core, LIGO is an incredibly precise instrument designed to detect the tiniest ripples in spacetime. It consists of two massive detectors located in the United States, one in Washington State and the other in Louisiana. Each detector is shaped like an L, with two arms stretching out for 4 kilometers in perpendicular directions. Inside these arms, powerful lasers bounce back and forth between mirrors suspended at each end. When a gravitational wave passes through Earth, it causes spacetime to stretch and squeeze ever so slightly. This distortion changes the distance between the mirrors and LIGO arms by an amount smaller than the width of a single proton. The lasers inside the arms detect this minuscule change, allowing scientists to measure the gravitational wave's presence. It's like trying to detect a ripple in a pond by measuring the distance between two floating leaves with the precision of a hair's breadth. The detection in 2015 came from the collision of two black holes, located 1.3 billion light-years away. The energy released during their merger sent ripples through spacetime that traveled across the universe, eventually reaching LIGO detectors. This discovery not only confirmed Einstein's theory, but also marked the beginning of a new era in astronomy, one where we can listen to the universe's most violent and energetic events. As we move forward, LIGO continues to scan the skies, capturing more gravitational waves and revealing the hidden stories of the cosmos. Each detection brings us closer to understanding the universe's most mysterious phenomena, from black holes to neutron stars and beyond. Through LIGO, we're not just observing the universe, we're listening to its symphony. Now turning to the cosmic dance of black hole mergers, let's dive deeper into the event that marked the first detection of gravitational waves. Imagine two black holes, each with masses tens of times greater than our Sun, locked in a spiraling embrace. Over millions of years, they orbit each other, drawing closer and closer, until finally, they collide in a cataclysmic explosion of energy. This collision, which occurred 1.3 billion light-years away, sent ripples through the fabric of spacetime, traveling across the universe until they reached LIGO detectors here on Earth. The process of a black hole merger is both violent and beautiful. As the two black holes spiral inward, they lose energy in the form of gravitational waves, causing their orbits to shrink faster and faster. In the final moments before the collision, they whirl around each other at nearly the speed of light, distorting spacetime itself. When they finally merge, they form a single, more massive black hole, releasing an astonishing amount of energy, equivalent to several times the mass of the Sun, converted into pure gravitational waves in a fraction of a second. This energy ripples outward, stretching and squeezing spacetime as it travels. The waves detected by LIGO in 2015 were the echoes of this incredible event, a cosmic symphony played out over billions of years. The merger not only confirmed Einstein's predictions, but also gave us a glimpse into the extreme physics of black holes, where gravity is so strong that even light cannot escape. Through these mergers, we're learning more about the universe's most mysterious objects. Each collision reveals new details about the nature of black holes, from their masses and spins to the way they warp spacetime. It's a reminder that even in the darkest corners of the cosmos, there's a story waiting to be told, a story written in the ripples of spacetime itself. As we continue to listen to these cosmic echoes, we're uncovering the secrets of the universe, one gravitational wave at a time. Now turning to another cosmic spectacle, let's explore the groundbreaking detection of gravitational waves from a neutron star collision in 2017. Unlike black hole mergers, which are invisible to traditional telescopes, this event was a dazzling display of both gravitational waves and light, marking a monumental leap in our ability to study the universe. Neutron stars are the incredibly dense remnants of massive stars that have exploded in supernova. Imagine a star so compact that a single teaspoon of its material would weigh billions of tons. When two neutron stars spiral toward each other, they create ripples in spacetime, just like black holes. But when they finally collide, the result is even more spectacular. The collision not only sends out gravitational waves, but also produces a brilliant burst of light across multiple wavelengths, from gamma rays to visible light. This event, detected by LIGO and Virgo, was a game changer for astronomy. For the first time, scientists could observe the same cosmic event using both gravitational waves and light. Telescopes around the world and in space turned their gaze to the collision, capturing the aftermath in unprecedented detail. The light revealed the formation of heavy elements like gold and platinum, forged in the fiery crucible of the collision. This discovery confirmed that neutron star collisions are cosmic factories, producing many of the precious metals found on Earth and throughout the universe. The significance of this detection cannot be overstated. It marked the dawn of multi-messenger astronomy, where gravitational waves and light work together to paint a fuller picture of cosmic events. By combining these two forms of observation, scientists can now study the universe in ways that were once unimaginable, unlocking new insights into the nature of matter, gravity, and the cosmos itself. As we continue to witness these extraordinary events, we're reminded of the interconnectedness of the universe and the power of human ingenuity to decode its mysteries. Each collision, each ripple, and each burst of light brings us closer to understanding the grand tapestry of existence. And with every discovery, we're not just observers, we're participants in the unfolding story of the cosmos. Now turning to another cosmic phenomenon, let's delve into the explosive deaths of massive stars and the gravitational waves they produce. Supernova, the spectacular final act of a star's life, are among the most energetic events in the universe. When a massive star exhausts its nuclear fuel, it can no longer support its own weight, leading to a catastrophic collapse. This collapse triggers a violent explosion, tearing the star apart and sending shock waves rippling through the fabric of spacetime. Imagine a star many times more massive than our Sun, reaching the end of its life. As its core collapses under its own gravity, it releases an immense amount of energy in a matter of seconds. This energy is so powerful that it outshines entire galaxies for a brief moment. But the explosion doesn't just produce light, it also generates gravitational waves. These waves are created as the star's core collapses asymmetrically, sending ripples through space-time that travel across the universe. Detecting gravitational waves from supernova is a challenging task, as the signals are often weaker than those from black hole or neutron star collisions. However, when a supernova occurs relatively close to Earth, observatories like LIGO and Virgo have the potential to pick up these faint ripples. Such detections would provide invaluable insights into the inner workings of these stellar explosions, revealing details about the star's structure, the dynamics of the collapse, and the formation of exotic objects like neutron stars or black holes. Supernovae are not just cosmic spectacles, they are also essential to the story of the universe. These explosions scatter heavy elements, forged in the hearts of stars, across space, seeding the cosmos with the building blocks of planets, life, and even us. By studying the gravitational waves they produce, we gain a deeper understanding of how these elements are created and distributed, and how the universe evolves over time. As we continue to explore the universe through the lens of gravitational waves, supernova remind us of the incredible forces at play in the cosmos. Each explosion is a testament to the dynamic and ever-changing nature of the universe, and each ripple in space-time brings us closer to unraveling its deepest mysteries. Now turning to the speed of gravitational waves, let's explore one of the most fascinating aspects of these cosmic ripples. According to Albert Einstein's theory of general relativity, gravitational waves travel at the speed of light, the fastest speed possible in the universe. This means that when a massive event like a black hole collision or a supernova occurs, the gravitational waves it produces race through space-time at the same speed as light itself. But how do we know this is true? The answer lies in a groundbreaking observation made in 2017. That year, scientists detected gravitational waves from the collision of two neutron stars. What made this event extraordinary was that it also produced light, which was observed by telescopes around the world. By comparing the arrival times of the gravitational waves and the light from the same event, researchers confirmed that both traveled at the same speed. The gravitational waves arrived first, followed by the light just moments later, matching Einstein's prediction with incredible precision. This discovery not only validated a key aspect of his theory, but also marked a new era in astronomy, where we can now observe cosmic events using both gravitational waves and light. The speed of gravitational waves has profound implications for our understanding of the universe. It tells us that these ripples in space-time are not just a theoretical concept, but a real, measurable phenomenon that behaves exactly as Einstein envisioned. It also means that when we detect gravitational waves, we are essentially witnessing events as they happened, in real time, across vast cosmic distances. This opens up exciting possibilities for studying the universe in ways we never thought possible, from probing the interiors of neutron stars to exploring the very fabric of spacetime itself. As we continue to unravel the mysteries of gravitational waves, their speed reminds us of the elegance and precision of the laws that govern our universe. Each ripple carries with it a story of cosmic events that occurred billions of years ago, traveling across the cosmos at the speed of light to reach us here on Earth. And with every detection, we come one step closer to understanding the grand tapestry of the universe and our place within it. Now turning to the global effort behind detecting gravitational waves, let's explore the network of observatories that work together to uncover the secrets of the universe. While the Laser Interferometer Gravitational Wave Observatory, or LIGO, in the United States is perhaps the most well-known, it is not alone in this groundbreaking mission. Across the globe, other detectors like Virgo in Italy and Kagra in Japan play a crucial role in this cosmic detective work. Together, these observatories form a powerful international collaboration, each contributing unique capabilities to the search for gravitational waves. Virgo, located near Pisa, Italy, is a key partner in this global network. Its advanced design and sensitivity allow it to detect gravitational waves with remarkable precision, complementing the data collected by LIGO. Similarly, Kagra, situated deep underground in the mountains of Japan, brings its own strengths to the table. By operating in a quieter seismic environment, Kagra can pick up faint signals that might otherwise be lost in the noise. These detectors, along with LIGO, create a triangulation effect, enabling scientists to pinpoint the exact location of gravitational wave sources in the sky with unprecedented accuracy. This global network is more than just a collection of observatories. It's a testament to the power of international collaboration in science. By sharing data and working together, researchers can cross-check their findings, reduce errors, and ensure that the signals they detect are genuine. This teamwork not only improves the accuracy of gravitational wave detections, but also allows scientists to study cosmic events in greater detail than ever before. For example, when a gravitational wave is detected, the combined data from LIGO, Virgo, and Kagra can help determine the exact direction of the source, making it easier for telescopes to follow up and observe the event in other wavelengths of light. As we look to the future, this global network will continue to expand, with new detectors being planned and existing ones upgraded. Each addition brings us closer to a more complete understanding of the universe, allowing us to explore phenomena like black hole mergers, neutron star collisions, and even the echoes of the Big Bang itself. The collaboration between these observatories is a shining example of how science transcends borders, uniting us in our quest to unravel the mysteries of the cosmos. And with every new detection, we take another step toward mapping the intricate dance of spacetime itself. Now turning to the challenges in detecting gravitational waves, let's explore the immense hurdles scientists must overcome to capture these elusive ripples in spacetime. Gravitational waves are incredibly faint, often dwarfed by the background noise of everyday vibrations like passing trucks, earthquakes, or even the wind. To detect such subtle signals, scientists must isolate their instruments from these disturbances with extraordinary precision. This requires engineering marvels that push the boundaries of human ingenuity. For instance, the detectors used in observatories like LIGO, Virgo, and Cagra are designed to measure distortions in spacetime that are smaller than 1/10,000th the width of a proton. To achieve this level of sensitivity, the mirrors inside these detectors are suspended on ultra-stable systems that can absorb and cancel out vibrations. Even the tiniest movement, like the footsteps of a person walking nearby, could disrupt the measurements. To combat this, the mirrors are isolated using advanced suspension systems and placed in vacuum chambers to eliminate interference from air molecules. Another challenge lies in the sheer complexity of the data. Gravitational wave signals are often buried within a sea of noise, requiring sophisticated algorithms to sift through the information and identify genuine cosmic events. Scientists must carefully analyze the data, cross-checking it with other detectors to confirm its validity. This process demands not only cutting-edge technology, but also a deep understanding of the physics behind gravitational waves. Despite these challenges, the precision and dedication of the teams behind these observatories have made groundbreaking discoveries possible. Each detection is a triumph of human ingenuity, showcasing our ability to overcome seemingly insurmountable obstacles in the pursuit of knowledge. As we continue to refine our techniques and expand our global network of detectors, we move closer to unlocking even more secrets of the universe, one ripple at a time. Now turning to the role of mathematics, let's dive into the intricate calculations and equations that make gravitational wave science possible. At the heart of this field lies Albert Einstein's field equations, a set of complex mathematical formulas that describe how massive objects warp the fabric of spacetime. These equations, first published in Einstein's general theory of relativity over a century ago, laid the groundwork for our understanding of gravitational waves. They show how the collision of black holes, neutron stars, and other massive events can send ripples through spacetime, traveling across the universe at the speed of light. But Einstein's equations are just the beginning. To detect and interpret gravitational waves, scientists rely on advanced mathematical models and simulations. These tools allow researchers to predict what gravitational wave signals should look like based on different cosmic events. For example, when two black holes spiral toward each other and merge, the resulting gravitational waves follow a specific pattern. By comparing these theoretical predictions with the data collected by detectors like LIGO, scientists can confirm the presence of gravitational waves and determine the properties of the objects that created them. The mathematics behind these simulations is incredibly complex, involving high-performance computing and algorithms that can process vast amounts of data. These models must account for the behavior of spacetime under extreme conditions, such as the intense gravitational fields near black holes. Even small errors in these calculations could lead to incorrect interpretations of the data, so precision is key. This is where the beauty of mathematics shines. It provides a universal language that allows us to decode the secrets of the cosmos. Beyond detection, Mathematics also helps us understand the broader implications of gravitational waves. For instance, by analyzing the signals from black hole mergers, scientists can test Einstein's predictions and explore whether his theory holds true under the most extreme conditions. These studies have already led to new insights, such as the discovery of intermediate mass black holes and the confirmation that gravitational waves travel at the speed of light. In essence, mathematics is the backbone of gravitational wave science, transforming abstract theories into tangible discoveries. It bridges the gap between the theoretical and the observable, enabling us to explore the universe in ways that were once thought impossible. As we continue to refine our mathematical tools and expand our understanding, we unlock new possibilities for unraveling the mysteries of the cosmos, one equation at a time. Now turning to the origins of the universe, let's explore how gravitational waves might hold the key to understanding the Big Bang itself. Primordial gravitational waves, if detected, would be ripples in spacetime created during the universe's earliest moments, just fractions of a second after the Big Bang. These waves would carry information about the conditions of the universe when it was unimaginably hot, dense, and rapidly expanding. Detecting them would be like finding a cosmic time capsule, offering a glimpse into the very beginning of everything we know. The idea is that during the Big Bang, the universe underwent a period of rapid expansion called inflation. This sudden stretching of space-time would have generated gravitational waves, imprinting them on the fabric of the cosmos. If we could detect these primordial waves, they would provide direct evidence of inflation and help us understand how the universe transitioned from a tiny, hot point to the vast, structured cosmos we see today. It's like listening to the echoes of the universe's first heartbeat. However, detecting these ancient waves is no easy task. They would be incredibly faint, having traveled across the universe for over 13.8 billion years. To find them, scientists are developing new technologies and missions, such as space-based observatories designed to search for these subtle signals. These efforts aim to measure the faint distortions in space-time left over from the Big Bang, offering a window into the universe's infancy. The implications of such a discovery would be profound. Primordial gravitational waves could reveal details about the fundamental forces and particles that shaped the early universe. They might even help us understand the nature of dark energy, the mysterious force driving the universe's accelerated expansion. By studying these waves, we could piece together the story of how the universe began and how it evolved into the complex, beautiful structure we observe today. In essence, primordial gravitational waves represent a direct link to the universe's birth. They hold the potential to answer some of the most profound questions in science, from the nature of inflation to the origins of cosmic structure. As we continue to search for these elusive signals, we edge closer to uncovering the secrets of the Big Bang and the very foundation of our existence. The quest to detect these ancient ripples is not just a scientific endeavor, it's a journey to the very beginning of time itself. Now turning to the mysteries of dark matter, let's explore how gravitational waves might shed light on this enigmatic substance that makes up most of the universe's mass. Dark matter is invisible It doesn't emit, absorb, or reflect light, yet its gravitational effects are undeniable. We see its influence in the way galaxies rotate and how massive structures in the universe form. But what exactly is dark matter, and how could gravitational waves help us uncover its secrets? One intriguing possibility is that dark matter interacts with gravity in ways we don't yet fully understand. If dark matter particles or objects, like primordial black holes, exist, they could produce gravitational waves when they collide or interact. These waves would carry information about the properties of dark matter, offering clues about its nature and behavior. Imagine detecting a gravitational wave signal that doesn't match the patterns of black holes or neutron stars. It could be the fingerprint of dark matter itself. Another avenue of exploration involves the way dark matter influences the propagation of gravitational waves. As these waves travel through the universe, they might be subtly affected by the presence of dark matter, altering their frequency or amplitude. By studying these changes, scientists could infer the distribution and density of dark matter in the cosmos. It's like using gravitational waves as a cosmic probe, mapping the invisible scaffolding of the universe. The connection between gravitational waves and dark matter also extends to the early universe. If dark matter played a role in the formation of the first stars and galaxies, its influence might be imprinted in the gravitational waves from that era. Detecting these ancient signals could reveal how dark matter shaped the universe's evolution, from its infancy to the complex web of galaxies we see today. While the search for dark matter through gravitational waves is still in its early stages, the potential is immense. These ripples in spacetime could unlock answers to one of the greatest mysteries in modern physics. By combining gravitational wave observations with other methods, like particle detectors and telescopes, we might finally piece together the puzzle of dark matter and its role in the cosmos. The journey to understand this elusive substance is far from over, but gravitational waves offer a promising new path forward. Now turning to the fascinating world of black holes, let's explore how gravitational waves have transformed our understanding of these cosmic giants. Black holes have long been shrouded in mystery, their intense gravity trapping even light itself. But thanks to gravitational waves, we're now peering into their secrets like never before. One of the most groundbreaking discoveries has been the confirmation of intermediate mass black holes. For decades, scientists knew about stellar mass black holes, formed from collapsing stars and supermassive black holes, lurking at the centers of galaxies. But the existence of black holes in between these sizes, intermediate mass black holes, was only a theory until gravitational waves provided the evidence. These waves, detected from collisions involving black holes tens of thousands of times more massive than our Sun, have filled a crucial gap in our understanding of black hole evolution. Gravitational waves have also given us unprecedented insights into the properties of black hole event horizons, the point of no return where gravity becomes so strong that nothing can escape. By analyzing the ripples from black hole mergers, scientists can study the behavior of spacetime near these boundaries. For instance, the ring-down phase of a gravitational wave signal, the final moments after two black holes merge, reveals how the newly formed black hole settles into its stable state. This process is like listening to the echoes of spacetime itself, telling us about the shape and stability of the event horizon. Another remarkable discovery involves the spin of black holes. Gravitational waves carry information about how fast black holes are rotating before they collide. Some black holes spin at nearly the speed of light, warping spacetime around them in dramatic ways. These observations have challenged our theories and deepened our understanding of how black holes form and grow. Perhaps most intriguing is the way gravitational waves have allowed us to test Einstein's theory of general relativity in the most extreme environments. Black holes are the ultimate laboratories for studying gravity, and every gravitational wave detection provides new data to confirm or challenge our current understanding. For example, the precise measurements of black hole mergers have so far aligned perfectly with Einstein's predictions, but future detections might reveal subtle deviations, hinting at new physics beyond our current knowledge. As we continue to detect more gravitational waves from black hole collisions, we're not just observing these cosmic events, we're unraveling the very fabric of spacetime. Each ripple brings us closer to understanding the true nature of black holes, from their formation to their role in shaping the universe. The journey is far from over, but with every new detection, we're rewriting the story of these enigmatic objects and their place in the cosmos. Now turning to the enigmatic interiors of neutron stars, let's explore how gravitational waves are shedding light on these incredibly dense cosmic objects. Neutron stars are the remnants of massive stars that have exploded in supernova, leaving behind cores so dense that a single teaspoon of their material would weigh billions of tons. Yet, despite their extreme density, much about their interiors remains a mystery. Gravitational waves are now helping us peer into these hidden depths. When neutron stars collide, they send ripples through spacetime that carry valuable information about their internal structure. These collisions are so violent that they distort the very fabric of the universe, creating gravitational waves that reveal details about the star's composition and behavior. For instance, the way neutron stars deform during a collision, known as their tidal deformability, can tell us about the nature of the matter inside them. This matter is so compressed that it exists in states we cannot replicate on Earth, making neutron stars natural laboratories for studying physics under extreme conditions. One of the key questions scientists are trying to answer is whether the cores of neutron stars contain exotic forms of matter, such as free quarks or hyperons. These particles, if they exist, would challenge our current understanding of nuclear physics. Gravitational waves provide a unique way to probe these possibilities. By analyzing the signals from neutron star mergers, researchers can infer the star's internal pressure and density, offering clues about the presence of these exotic states. Another fascinating aspect is the role of gravitational waves in understanding the equation of state of neutron stars, the relationship between their pressure and density. This equation determines how stiff or soft neutron star matter is, influencing how much a neutron star can deform before collapsing into a black hole. Gravitational wave observations from events like the merger of two neutron stars in 2017 have already provided groundbreaking data, narrowing down the possible equations of state and bringing us closer to solving this cosmic puzzle. Moreover, the study of neutron star interiors through gravitational waves has implications beyond astrophysics. It connects to fundamental questions about the nature of matter and the forces that govern it. For example, understanding how matter behaves at such extreme densities could shed light on the strong nuclear force which binds atomic nuclei together. This force is one of the least understood in physics, and neutron stars offer a unique window into its behavior. As we continue to detect gravitational waves from neutron star collisions, we're not just observing these cosmic events, we're unlocking the secrets of matter itself. Each ripple carries a wealth of information, helping us piece together the puzzle of what lies inside these mysterious objects. With every new detection, we're stepping closer to understanding the universe's most extreme environments and the fundamental laws that shape them. Now turning to the vast expanse of the cosmos, let's explore how gravitational waves are helping us measure the expansion of the universe. One of the most profound questions in astronomy is understanding how fast the universe is growing. This rate of expansion is described by the Hubble constant, a number that tells us how quickly galaxies are moving away from each other as the universe stretches. But here's the twist: scientists have been debating the precise value of the Hubble constant for decades, and gravitational waves might just hold the key to resolving this cosmic mystery. When two massive objects, like neutron stars or black holes, collide, they send out gravitational waves that ripple through spacetime. These waves carry information about the distance to the collision event. If astronomers can also observe the light from the same event, like they did with the neutron star merger in 2017, they can measure the speed at which the event's host galaxy is moving away from us. By combining these two pieces of information, scientists can calculate the Hubble constant with remarkable precision. This method is independent of traditional techniques, which rely on observing distant stars or the cosmic microwave background, making it a powerful new tool in the quest to understand the universe's expansion. The beauty of using gravitational waves lies in their ability to provide a direct measurement of distance. Unlike light, which can be dimmed or distorted by dust and gas, gravitational waves travel unimpeded through the cosmos, offering a clear signal. This makes them an ideal tool for measuring cosmic distances and, by extension, the Hubble constant. However, the results from gravitational wave observations have added fuel to the ongoing debate. Some measurements suggest a faster expansion rate, while others point to a slower one. This discrepancy, known as the Hubble tension, has left scientists puzzled and eager to gather more data. The implications of resolving this tension are enormous. The Hubble constant isn't just a number, it's a cornerstone of our understanding of the universe's history and future. A precise value could help us determine the age of the universe more accurately, shed light on the nature of dark energy, and even reveal new physics beyond our current theories. Gravitational waves, with their unique ability to probe the cosmos, are poised to play a central role in this quest. As we continue to detect more gravitational wave events, Each one brings us closer to unraveling the mystery of the universe's expansion. These ripples in space-time are not just echoes of cosmic collisions, they are messengers, carrying clues about the very fabric of reality. With every new detection, we're not just measuring distances, we're charting the course of the universe itself, one ripple at a time. Now turning to the horizon of discovery, let's explore the future of gravitational wave astronomy and the exciting missions that promise to deepen our understanding of the universe. One of the most anticipated projects is the Laser Interferometer Space Antenna, or LISA, a groundbreaking mission set to launch in the next decade. Unlike ground-based detectors like LIGO, LISA will operate in space, free from the vibrations and noise of Earth, allowing it to detect gravitational waves at much lower frequencies. This opens up a whole new window into the cosmos, enabling us to observe events that ground-based detectors simply cannot see. LISA will consist of 3 spacecraft, flying in a triangular formation, separated by millions of kilometers. These spacecraft will use lasers to measure tiny changes in distance caused by passing gravitational waves. By operating in space, LISA will be able to detect waves from some of the most massive and distant objects in the universe, such as supermassive black hole mergers and the early stages of galaxy formation. These observations could provide unprecedented insights into the evolution of the universe and the nature of spacetime itself, but LISA is just the beginning. Other missions, like the Einstein telescope and Cosmic Explorer, are also in development. These next-generation ground-based detectors will be even more sensitive than LIGO, capable of detecting gravitational waves from events that are currently beyond our reach. Together, these missions will create a global network of observatories, working in harmony to map the gravitational wave sky and uncover the secrets of the universe. The potential discoveries from these missions are staggering. They could reveal the existence of intermediate mass black holes, shed light on the mysterious interiors of neutron stars, and even detect gravitational waves from the very first moments after the Big Bang. Each new mission brings us closer to answering some of the most profound questions in science, from the nature of dark matter to the ultimate fate of the universe. As we look to the future, it's clear that gravitational wave astronomy is just getting started. With every new mission, we're not just expanding our toolkit, we're opening new chapters in the story of the cosmos. These ripples in space-time are more than just signals. They are keys to unlocking the mysteries of the universe, and the best is yet to come. Now turning to the next frontier in our cosmic exploration, let's delve into the exciting world of multi-messenger astronomy, where gravitational waves play a starring role. This revolutionary approach combines data from multiple sources, light, particles, and gravitational waves, to paint a fuller picture of the universe's most dramatic events. Imagine trying to understand a story by reading only one page of a book. Multi-messenger astronomy allows us to read the entire chapter, giving us a richer, more complete understanding of cosmic phenomena. One of the most remarkable examples of this approach came in August 2017, when astronomers detected gravitational waves from the collision of 2 neutron stars. But this time, it wasn't just gravitational waves. Telescopes around the world also observed the event in visible light, X-rays, and gamma rays. This was the first time in history that a cosmic event was observed using both gravitational waves and electromagnetic radiation, marking a monumental leap in our ability to study the universe. The data revealed details about the formation of heavy elements like gold and platinum, providing insights into the origins of the very materials that make up our world. Multi-messenger astronomy doesn't stop there. It also incorporates observations of neutrinos, tiny particles that travel through space, almost unaffected by matter. When a star explodes as a supernova, for instance, it releases a flood of neutrinos alongside light and gravitational waves. By combining these signals, scientists can piece together the intricate processes happening inside these cataclysmic events. This collaborative approach has transformed astronomy into a truly global effort, with researchers from different fields and countries working together to decode the universe's secrets. The beauty of multi-messenger astronomy lies in its ability to bring together diverse tools and perspectives. Gravitational waves give us a new way to listen to the universe, while light and particles allow us to see and feel it. Together, they create a symphony of data that reveals the hidden workings of the cosmos. This collaborative spirit is at the heart of modern astronomy, reminding us that the quest to understand the universe is a shared endeavor, uniting humanity in the pursuit of knowledge. As we continue to refine our tools and techniques, multi-messenger astronomy promises to unlock even more secrets of the cosmos. From the birth of black holes to the origins of the elements, this approach is reshaping our understanding of the universe, one observation at a time. And with each discovery, we're reminded that the universe is far more interconnected and far more wondrous than we ever imagined. Now turning to the fascinating world of sound, let's explore how scientists have found a way to hear the universe through gravitational waves. Just as a musical instrument creates sound waves that travel through the air, cosmic events, like black hole collisions, produce ripples in spacetime that can be translated into sound. This process allows us to experience the universe in a completely new way, not just through images or data, but through the eerie, otherworldly sounds of these distant events. When gravitational waves are detected by instruments like the Laser Interferometer, Gravitational Wave Observatory, or LIGO, the signals are incredibly faint. To make them audible, scientists shift the frequencies of these waves into a range that human ears can hear. The result is a series of chirps, thuds, and hums that represent the collisions of black holes, the merging of neutron stars, and other cosmic phenomena. For example, the first detected gravitational waves from two black holes colliding produced a distinctive chirp sound, a brief, rising tone that marked the moment the black holes spiraled together and merged. These sounds are more than just scientific curiosities. They're a window into the dynamics of the universe. The pitch, duration, and intensity of these cosmic sounds reveal details about the objects involved, such as their masses, distances, and how they interact. A black hole merger might produce a sharp, high-pitched chirp, while a neutron star collision could create a longer, more complex sound. Each event has its own unique voice, adding to the growing symphony of the cosmos. The idea of cosmic symphonies isn't just poetic, it's a powerful way to think about the universe. Just as a symphony combines different instruments to create a rich, layered piece of music, the universe combines gravitational waves, light, and particles to tell its story. By listening to these sounds, we're not just observing the universe, we're experiencing it in a deeply human way. It's a reminder that science isn't just about numbers and equations. It's about connecting with the mysteries of the cosmos on a sensory level. As we continue to refine our ability to detect and interpret these sounds, we're opening up new possibilities for understanding the universe. From the haunting echoes of black hole collisions to the subtle whispers of neutron star mergers, the sounds of gravitational waves are transforming how we explore the cosmos. And with each new note we hear, we're reminded that the universe is not just something we see, it's something we can listen to too. Now turning to the realm of imagination and possibility, let's explore the intriguing connection between gravitational waves and time travel. While gravitational waves themselves are ripples in spacetime caused by massive cosmic events, they also open the door to fascinating theoretical ideas about how spacetime might be manipulated. One of the most captivating concepts is the idea that extreme distortions in spacetime, like those created by black holes or neutron stars, could potentially create pathways through time. Imagine spacetime as a vast, flexible fabric. Gravitational waves are like ripples moving across this fabric. But what if the fabric could be twisted or folded in such a way that it creates shortcuts? This is the essence of the theoretical concept known as a wormhole, a hypothetical tunnel through spacetime that could connect two distant points or even different moments in time. While wormholes remain purely theoretical, the extreme conditions that produce gravitational waves, such as black hole mergers, are the kinds of events that might make such phenomena possible. The idea of time travel has long captured the human imagination, from science fiction stories to serious scientific discussions. Gravitational waves add a new layer to this conversation. If spacetime can be warped enough to create ripples, could it also be warped enough to create loops or bridges through time? Some theories suggest that under the right conditions, the intense gravitational fields of colliding black holes or neutron stars might create temporary distortions that could, in theory, allow for time travel. Of course, this remains speculative, but it's a thrilling area of exploration that combines the science of gravitational waves with the boundless possibilities of theoretical physics. What makes this connection even more fascinating is that gravitational waves themselves travel at the speed of light, as predicted by Einstein. This means they are intimately tied to the fabric of spacetime and its behavior. If we could one day harness or manipulate gravitational waves, could we also find a way to navigate through time? While this remains a distant dream, the study of gravitational waves continues to push the boundaries of our understanding, reminding us that the universe is full of mysteries waiting to be uncovered. As we ponder these ideas, it's important to remember that science often begins with imagination. The connection between gravitational waves and time travel may be speculative, but it sparks curiosity and wonder, driving us to ask deeper questions about the nature of reality. And who knows, perhaps one day, the ripples in spacetime that we detect today will lead us to discoveries that redefine our understanding of time itself. For now, we can let our imaginations wander, inspired by the cosmic symphony of gravitational waves and the endless possibilities they represent. Now turning to the stars and the possibility of life beyond our planet, let's explore the fascinating idea of gravitational waves and alien civilizations. Could advanced extraterrestrial beings detect or even produce these ripples in space-time? And if so, might they use gravitational waves as a means of communication across the vast distances of the universe? Imagine a civilization far more advanced than our own, one that has mastered the intricacies of space-time itself, just as we have built detectors like LIGO to listen for the faint whispers of gravitational waves. Such a civilization might have developed technology far beyond our comprehension to not only detect these waves, but also to create them intentionally. Gravitational waves, traveling at the speed of light and unaffected by the dust and gas that obscure light, could serve as an ideal medium for interstellar communication. Unlike radio waves, which can be scattered or absorbed, gravitational waves could carry messages across galaxies with minimal interference. But how might this work? One possibility is that an advanced civilization could manipulate massive objects, like neutron stars or black holes, to produce specific patterns of gravitational waves. These patterns could encode information, much like Morse code, allowing for the transmission of complex messages. The idea of using gravitational waves as a cosmic telegraph is both thrilling and humbling, reminding us of the vast potential for discovery that lies beyond our current understanding. Of course, this raises the question, if such civilizations exist, why haven't we detected their signals? One answer lies in the immense challenge of detecting and interpreting gravitational waves. Even with our most advanced technology, we are only just beginning to hear the faintest echoes of these cosmic ripples. It's possible that the gravitational wave signals from alien civilizations are simply too subtle or too distant for us to detect, at least for now. As we ponder these possibilities, it's worth considering how the study of gravitational waves might one day connect us to other intelligent beings in the universe. The search for extraterrestrial life has long focused on radio signals and light, but gravitational waves open a new frontier in this quest. They remind us that the universe is full of mysteries and that our understanding of it is still in its infancy. Moving forward, the exploration of gravitational waves and their potential role in interstellar communication invites us to dream bigger and think beyond the limits of our current knowledge. Whether or not we ever detect signals from alien civilizations, the very idea challenges us to expand our horizons and consider the profound ways in which we are connected to the cosmos. And who knows, perhaps one day, the ripples in space-time will carry not just the echoes of colliding black holes, but the voices of beings from worlds far beyond our own. Now turning to the influence of gravitational waves on popular culture, let's explore how these cosmic ripples have captured the imagination of storytellers, artists, and creators across the globe. Gravitational waves, with their mysterious and awe-inspiring nature, have become a source of inspiration for movies, books, and art, shaping how we envision the universe and our place within it. In science fiction, gravitational waves often serve as a gateway to exploring the unknown. Films like Interstellar have brought the concept of spacetime and its distortions to life, using stunning visuals to depict black holes and the warping of reality. These portrayals not only entertain, but also spark curiosity, encouraging audiences to ponder the deeper mysteries of the cosmos. Books, too, have embraced gravitational waves as a central theme, weaving them into narratives that blend hard science with imaginative storytelling. Authors use these ripples in space-time to craft tales of interstellar travel, alien civilizations, and the very fabric of reality itself. Artists, meanwhile, have found in gravitational waves a muse for their creativity. From abstract paintings that capture the undulating patterns of space-time to sculptures that evoke the collision of massive cosmic objects, gravitational waves have inspired works that bridge the gap between science and art. These creations invite us to see the universe not just through the lens of equations and data, but as a place of beauty and wonder. Even beyond fiction and art, gravitational waves have influenced how we think about our place in the cosmos. They remind us that the universe is a dynamic, ever-changing place, full of phenomena that challenge our understanding and expand our imagination. By bringing these concepts into popular culture, gravitational waves have become more than just a scientific discovery. They are a symbol of humanity's endless curiosity and our desire to explore the unknown. As we reflect on the impact of gravitational waves in popular culture, it's clear that they have done more than just advance our scientific knowledge. They have sparked a sense of wonder and possibility, inspiring us to dream of what lies beyond the stars. And as we continue to explore the mysteries of the universe, gravitational waves will undoubtedly remain a source of inspiration, shaping not only our understanding of the cosmos, but also the stories we tell about it. Now turning to the beauty of gravitational waves, let's take a moment to appreciate not just their scientific significance, but also their profound aesthetic and philosophical impact. Gravitational waves are more than just ripples in spacetime. They are a testament to the elegance and harmony of the universe. These waves, born from the most violent and energetic events in the cosmos, carry with them a kind of cosmic poetry, reminding us of the delicate balance and interconnectedness that underlies everything. Imagine the universe as a vast, intricate tapestry, woven together by the forces of gravity, light, and time. Gravitational waves are like the threads that ripple through this tapestry, connecting distant stars, galaxies, and even the very fabric of existence itself. They show us that no event in the universe happens in isolation. The collision of two black holes billions of light years away sends ripples that eventually reach us, a gentle reminder that we are part of something much larger than ourselves. There's a certain beauty in the way gravitational waves reveal the hidden rhythms of the cosmos. They are like the universe's heartbeat, pulsing with the energy of creation and destruction. Each wave carries the story of its origin, a story of immense power, of stars collapsing, of black holes merging, of the very fabric of spacetime being stretched and squeezed. And yet, despite their violent beginnings, these waves travel across the universe with a kind of serene grace, arriving at our detectors as faint whispers from the depths of space. This beauty isn't just visual or scientific, it's deeply philosophical Gravitational waves remind us that the universe is a dynamic, ever-changing place, where even the most distant events can have a profound impact on our understanding of reality. They challenge us to think beyond the limits of our own experience, to consider the vastness of time and space, and to reflect on our place within this grand cosmic dance. In a way, gravitational waves are a bridge between the scientific and the spiritual. They invite us to marvel at the mysteries of the universe, to embrace the unknown, and to find meaning in the interconnectedness of all things. They remind us that we are not just observers of the cosmos, but active participants in its unfolding story. As we contemplate the beauty of gravitational waves, we are reminded of the profound truth that the universe is not just a collection of objects and forces, but a living, breathing entity full of wonder and possibility. And in this realization, we find not just knowledge, but a deeper sense of connection to the cosmos and to each other. Now turning to the role of human curiosity in the study of gravitational waves, let's reflect on what drives us to explore the unknown. Gravitational waves are not just a scientific breakthrough, they are a testament to humanity's unquenchable thirst for knowledge and our relentless desire to understand the universe. From the earliest stargazers to the modern scientists who built LIGO, our species has always looked to the skies with wonder, asking questions about our place in the cosmos. Gravitational waves are the latest chapter in this age-old quest, offering us a new way to listen to the universe and decode its secrets. The discovery of gravitational waves has had a profound emotional and intellectual impact on us. On one level, it's a triumph of human ingenuity, a reminder of what we can achieve when we combine curiosity, creativity, and collaboration. It took decades of effort, countless hours of research, and the combined expertise of scientists from around the world to detect these faint ripples in spacetime. And yet, the moment that first signal was detected, it wasn't just a victory for science. It was a moment of awe and inspiration for all of humanity. It reminded us that the universe is full of mysteries waiting to be uncovered, and that we have the tools and the determination to uncover them. But gravitational waves also challenge us intellectually. They force us to rethink our understanding of space, time, and gravity. They push the boundaries of what we thought was possible, revealing new layers of complexity in the cosmos. Each new detection brings with it a flood of questions. What happens inside a black hole? How do neutron stars behave under extreme conditions? What can gravitational waves tell us about the origins of the universe? These questions don't just drive scientific progress, they spark our imagination and deepen our sense of wonder. At the same time, the study of gravitational waves connects us to something larger than ourselves. It reminds us that we are part of a vast, interconnected universe, where even the most distant events can have a ripple effect on our understanding of reality. This realization is both humbling and empowering. It humbles us by showing us how small we are in the grand scheme of things, but it also empowers us by showing us that we are capable of understanding and exploring the cosmos in ways that were once unimaginable. In the end, the study of gravitational waves is more than just a scientific endeavor. It's a reflection of who we are as a species. It's a reminder that curiosity is at the heart of what makes us human, and that our desire to explore and understand the universe is one of our greatest strengths. As we continue to listen to the whispers of spacetime, we are not just uncovering the secrets of the cosmos, we are also uncovering the depths of our own potential. And in this journey of discovery, we find not just answers, but a deeper connection to the universe and to each other. Now turning to the future of science, let's explore how gravitational wave research might revolutionize our understanding of the universe and drive technological advancements. The detection of gravitational waves has already opened a new window into the cosmos, but this is just the beginning. As we refine our ability to observe these ripples in space-time, we stand on the brink of discoveries that could reshape physics, astronomy, and even our everyday lives. One of the most exciting possibilities is the potential to uncover new physics beyond Einstein's theory of relativity. While general relativity has been incredibly successful in explaining gravity, there are still unanswered questions about how it fits with quantum mechanics. Gravitational waves could provide clues to this puzzle, helping us bridge the gap between these two fundamental theories. Imagine a future where we not only detect gravitational waves, but also use them to test theories of quantum gravity, revealing the true nature of spacetime at the smallest scales. In astronomy, gravitational waves are already transforming how we study the universe. Future detectors, like the Laser Interferometer Space Antenna, or LISA, will allow us to observe gravitational waves from even more distant and exotic sources. We might detect waves from the earliest moments of the Big Bang, offering a glimpse into the birth of the universe itself, or we could uncover signals from entirely new phenomena like cosmic strings or exotic compact objects that challenge our current understanding of astrophysics. But the impact of gravitational wave research extends beyond pure science. The technologies developed to detect these faint signals are pushing the boundaries of engineering and precision measurement. The lasers, mirrors, and vibration isolation systems used in detectors like LIGO are marvels of innovation, and their applications could extend far beyond astronomy. For example, the same techniques used to measure tiny spacetime distortions could lead to breakthroughs in medical imaging, earthquake detection, or even quantum computing. Moreover, the collaborative nature of gravitational wave research is setting a new standard for international scientific cooperation. Projects like LIGO, Virgo, and CAGRA involve thousands of scientists from dozens of countries working together to achieve a common goal. This spirit of collaboration could inspire future projects in other fields, fostering a global approach to solving humanity's greatest challenges. As we look ahead, it's clear that gravitational wave research has the potential to transform not just our understanding of the universe, but also the way we live and work. It's a reminder that the pursuit of knowledge is not just about answering abstract questions. It's about pushing the boundaries of what's possible and creating a better future for all of us. And as we continue to explore the cosmos through the lens of gravitational waves, we are not just uncovering the secrets of the universe, we are also shaping the future of science itself. Now turning to the deeper questions that gravitational waves inspire, let's reflect on how these cosmic ripples connect us to the vastness of the universe and our search for meaning. Gravitational waves are more than just scientific phenomena. They are a reminder of our place in the cosmos. Each time we detect these faint signals, we are witnessing events that occurred billions of years ago, in galaxies far beyond our own. It's a humbling experience, one that invites us to ponder the scale of existence and our role within it. The study of gravitational waves also touches on something deeply human, our desire to understand the universe and our place within it. For centuries, humans have looked to the stars for answers, seeking patterns, purpose, and meaning in the cosmos. Gravitational waves offer a new way to explore these age-old questions. They allow us to listen to the universe itself, to hear the echoes of black holes colliding, neutron stars merging, and stars exploding. In these sounds, we find not just data, but a connection to the grand narrative of the cosmos. There's something profoundly spiritual about this connection. Gravitational waves remind us that the universe is dynamic, ever-changing, and full of mysteries waiting to be uncovered. They show us that even the most violent and chaotic events, like the collision of black holes, can create something beautiful and meaningful. In a way, these waves are like cosmic messengers, carrying stories from the farthest reaches of space and time, stories that resonate with our own search for understanding. But gravitational waves also challenge us to confront the limits of our knowledge. They remind us that the universe is far more complex and mysterious than we can fully comprehend. This realization can be both humbling and inspiring. It invites us to embrace curiosity, to keep asking questions, and to remain open to the possibility that the answers we seek may be stranger and more wonderful than we can imagine. Ultimately, the study of gravitational waves is not just about science, it's about what it means to be human. It's about our capacity to wonder, to explore, and to find meaning in the vastness of the cosmos. As we continue to listen to the whispers of spacetime, we are not just uncovering the secrets of the universe, we are also discovering more about ourselves. And in that discovery, we find a deeper connection to the universe and to each other, a connection that transcends time, space, and the boundaries of our understanding. Now turning to the conclusion of our journey through the science and wonder of gravitational waves, let's take a moment to reflect on what we've explored. We began by uncovering the basics of these cosmic ripples, how they are born from the most violent and energetic events in the universe, black hole collisions, neutron star mergers, and the explosive deaths of massive stars. We learned how Einstein's genius predicted their existence long before technology could detect them, and how instruments like LIGO and Virgo have opened a new window into the cosmos, allowing us to listen to the universe in a way never before possible. We delved into the profound implications of these discoveries, from reshaping our understanding of black holes and neutron stars to offering clues about the universe's expansion and even its origins. Gravitational waves have not only deepened our knowledge of the cosmos, but also sparked new questions, reminding us that the universe is full of mysteries waiting to be unraveled. They've shown us that even in the chaos of colliding black holes, there is beauty and meaning, a cosmic symphony that echoes across space and time. But beyond the science, gravitational waves have touched something deeper within us, our innate curiosity and desire to understand our place in the universe. They've reminded us that we are part of a vast, interconnected cosmos, one that is dynamic, ever-changing, and full of wonder. Each detection is a humbling reminder of how small we are in the grand scheme of things, yet how extraordinary it is that we can witness these events at all. As we bring this exploration to a close, let these thoughts linger in your mind. Picture the universe as a vast, shimmering tapestry, woven with the threads of spacetime, where every ripple tells a story. Let the idea of gravitational waves carry you into a state of calm and reflection, inviting you to dream of the cosmos as you drift off to sleep. Imagine the distant echoes of black holes colliding, the gentle hum of neutron stars dancing, and the faint whispers of the universe's earliest moments. Let these cosmic stories remind you of the beauty, mystery, and infinite possibilities that surround us. Thank you for joining me on this journey through the science and wonder of gravitational waves. If you enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell so you never miss a cosmic story. Until next time, keep looking up, keep wondering, and let the universe inspire your dreams.